Check, check, check. Are we good? Okay, are we ready? And live. I do want the announcer. I wonder if I can call the voiceover announcer for the Colbert Late Show. Stephen Colbert and I are very similar. We have the same sense of humor. We're about the same age, I think. I think he was, and I think like very close to even the same month. He might be a year older, but we're both born in May or something. Anyway, but we have the same sense of humor. I laugh hysterically at everything he's done all the way back from before you guys were born. I guess the Colbert Report might be before you guys. But it would be great to have his voiceover give us a recording for the show opening. I guess a year ago we could have got John Baptiste to record our opening. Probably be like one of the Cal fight songs. Get John Baptiste to add it up. But now he's won like an Oscar and a couple Emmys and Grammys and a Peabody. So can't go near that guy anymore. So welcome. We are here, day of the midterm. Midterm is this evening at 6 p.m. to 7:30 p.m. We have the alternate time for the overseas people tomorrow morning at 6 a.m. Everybody will be done by the time we meet here tomorrow at 8. The exam is 30-ish questions again, 35 points. Some questions worth a couple more. And as you know, the points are all just individual points. We're going to scale them to the numbers in the course information at the end of the course. And as you know, we're going to change the weighting slightly on the first midterm and move it towards the second and third midterms. So that will happen. This exam has one attempt. So these exams have been set up so you had 3 attempts, and that was to allow for a computer crash or something that was unavoidable. So you can get right back on and start again in case the computer, technical difficulties. That is not the case this time. There is one attempt allowed. So if one of those things do happen, and you have to stop the exam for some reason beyond your control, then email the staff, probably your GSI, your UGSI in particular, someone you know, get a response, and we can reset and give you another attempt in real time. So that's going to be important. So we'll be moderating the exam and looking for problems. And I will say again, as we moderate, the system does tell us kind of what you're doing. It's really kind of fancy. So try to avoid the suspicious looking activity, clicking around a lot and leaving the exam, coming back, leaving B courses, coming back. You'll have to do that to a certain extent because we give you an equation sheet and we give you the figures on the exam. So the figures on the exam are available 3 ways, I think, at least 3 ways. The exam's the same format, so you have a figure diagram table and then several questions related to it. So those in each of those figures or diagrams this time, you'll be able to click on a view in page HTML link, and that will open that figure in a separate B courses page in a new tab. So you can pull that tab out of your browser, or you can switch to a new window, or you can switch between those tabs in your browser. It's also available in the instructions, all the figures in one PDF. So you can have that open in a separate tab. So that's to help you, as you know, have that in front of you since the exam scrolls. So take advantage of those things that will help you work. Get your periodic table open, get your figures open, get your equation sheet open. You can have the exam and the periodic table open, excuse me, the equation sheet and the periodic table open in advance because they're always available, but they are also available in the instructions portion of the midterm. So is that it? Anything else in general I should say about the midterm this evening? We're going to review today and talk a little bit about the material we've covered, and we'll center ourselves again on our master diagram for the course. So what are we trying to accomplish? We're trying to accomplish understanding everything that we just, oh, darn it. I just launched my pen. Shoot. Sorry, it's back there somewhere. Everything about this diagram that we can in these 8 weeks of craziness that we call Summer Chem 1A. So we have gone through the thermodynamics, and now that has come back in, has folded back in for this midterm, because now we understand individual bond energies. We understand a great deal about the bonding. So we understand the order, magnitude of the bonding, the bond angles, and the structures. All of those things come into play in a chemical reaction. So on this exam, you'll be given molecules and asked to write Lewis dot structures and then infer a lot from Lewis dot structures: bond angles, bond orders, oxidation numbers, relative bond strengths, because we understand bond order and bond strength correlate. And that makes sense. Double, single, triple bonds, stronger relative bonds. But we also understand that in terms of the thermodynamics. We looked at bond enthalpies, energies of individual bonds. And we saw how that related to the reaction enthalpy. So that was a very important relationship. So this distance, if this is enthalpy platted here, then the enthalpy of the reaction is this difference in energy. And that difference in energy is a state function. It doesn't matter how I get from products to reactants. And importantly, that meant I could take this crazy path where I bust all these up into atoms, go from hydrogen and oxygen molecules to hydrogen and oxygen atoms, and then recombine the atoms to form the molecules. That's a different path than the molecules colliding and somehow rearranging. But enthalpy is a state function, so it doesn't matter. So if I take bond broken minus bonds formed in bond energies, which are always positive, then that should equal the enthalpy of the reaction. And at this point, I wish I had my pen because I wanted to do some annotations. I'll use, I can use my finger, but I've grown to like the pen. Actually, you can use any piece of plastic, as I recall. Let me try that. Can I do that? So this is an H bond, and this is an O bond. And now we can write a great deal down about those bonds, and we're going to form this H2O molecule. And we understand two linear molecules forming a bent molecule. That molecule has a permanent dipole moment. There is charge separation, a little bit of negative charge and a little bit of positive charge on the hydrogens. So that gives us that permanent dipole moment that we draw going from the plus to the minus. These molecules perfectly symmetric, no dipole moments. So the overall dipole moment increases as we go. The sample reacts more to an electric field as the reaction goes. But breaking those bonds and forming those bonds, in this case, releases energy. So breaking one oxygen double bond and two hydrogen single bonds requires less energy than forming two, in this case, 4 total hydrogen oxygen bonds, because I formed 2 moles of H2O. So I break all the bonds, but forming the bonds releases energy. If you take nothing else home from Chem 1, take home the fact breaking bond always requires energy, therefore forming always releases energy. We can correlate then bond energies and bond strengths and enthalpies of reaction. So that also tells us something about this second pathway, this catalyzed pathway. We understand now more deeply why this part does not change. The enthalpy of the reaction does not change. The activation energy changes. And we understand that because we know that energies are deeply related to the bonds breaking and bonds forming, which a catalyst does not affect. That's a state function. The energy is in the bonds. The catalyst accelerates the reaction by lowering the activation barrier. But if I'm forming and breaking bonds, it doesn't matter how I do that. That energy has to be absorbed and released, and the thermodynamics does not change. So a lot of important chemistry we got there. We understood this bond in great detail from the molecular orbitals, and we were able to tell that this oxygen is paramagnetic. You can switch back and forth between the board as I'm writing and the camera, if you'd like, Sydney. That isn't obvious from the Lewis dot structure. Those look like all paired electrons. Paramagnetic means there's unpaired electrons, at least one. And the magnitude of the paramagnetism increases with the number of unpaired electrons. So we have very deep understanding of everything that's going on, of much of what's going on up there. We looked at isomers and complicated, well, not necessarily complicated, but sophisticated shapes. So we had tetrahedra and square planar and pyramidal, bipyramidal, octahedral, all kinds of shapes. And we had the intuition, we're starting to get the intuition. Those shapes matter for a lot of reasons. The rates of reaction, we've said this a couple times, depend on the orientation of things coming in and colliding with each other. And that orientation can be very subtle. We saw chiral isomers. Handedness matters in a reaction. This reaction may go, let's say, if that's a chemical reaction, that's the favorable interaction, a right and left hand coming together. But two rights could not do that. They would not have those fingers overlapping like that. So the right and right, I only have one of each, sorry. So I can't bring those in together, but the orientation matters deep down to that subtle mirror image kind of chiral orientation. That is embodied here in the activation barrier. So the orientations of the molecules, the arrangements, their structures affect this. Their bonding affects this, the strength of the bonds. Doesn't matter if you're tetrahedral and you have a carbon-hydrogen bond, or you're planar and have a carbon-hydrogen bond, you still have a carbon-hydrogen bond you have to break. And that's unaffected by the angle. So here we have bond strengths. And here we have geometry. Okay? So beautiful understanding and a deep, deep understanding of what's going on in this diagram on a lot of levels. We also talked about, we'll get rid of some of that. We also talked about these reactions occurring in the gas phase, and now we understand a lot about the gas phase. So we talked about this being hydrogen and oxygen forming water. These are gases at room temperature. So we know 2 moles and 1 mole goes to 2 moles. If these are all gases, that corresponds to 2 atmospheres of gas, 1 atmosphere of gas and 2 atmospheres of gas, or that ratio of pressures, 2 to 1 to 2. The ratio of pressures and the ratio of moles is the same because PV, pressure times the volume of a gas, is nRT. So P, the pressure, and N, P, directly proportional to N, the number of moles. So I can use concentrations at constant volume, pressures at constant volume, the number of moles. All of them have the same stoichiometric relationship. So that again told us part about this. So this is governed by PV equals nRT. And that's a good chem quiz. Oh, these are good chem quizzes. I'm going to have to remember this. These are good, actually. These are really good exam questions. These exact exam questions aren't here, but it would be a great kind of exam question to say what factors affect the thermodynamics and what factors affect the kinetics. I love that. Look for that on the final because I didn't do it here. Here, and this is a couple of these factors might affect up here too, but this matters because of that. Energy is an extensive property. The more moles I burn, the more energy is released. So that is a thermodynamic constant. Burn more hydrogen, burn more fuel, more energy is released. That's why we do these things per mole. So you don't have to keep changing for every mole that you have. So in general, for this reaction, we catalog them when N is 1, so we don't have to keep changing that. This part of the reaction depends on the other aspect of gas that we talked about a great deal, and that was the distribution of we did it mostly for speeds of the particles versus the number of particles. So we said, well, if you're going to have reactions, they depend on collisions. If they depend on collisions, the faster we're moving on average, the more collisions we have. The more collisions we have, the faster the reaction can potentially go. Now, a faster reaction doesn't have to change the profile here. What it means is more. If you are higher up on this curve, so we know this plots velocities or speeds, but we know the energies are related to the speeds. So this is also a measure of energy. So the greater number of particles, so if we look at an energy here, the more particles I have with an energy that's greater than this energy, the faster that reaction will go. That didn't change the height. That just gave me more candidates to get over the barrier. So we saw that beautifully. And that explains to us the reaction dependence on temperature. So here is a temperature T, and here's a temperature T. And you should know for the exam tonight, which of those is the higher temperature. You should be able to interpret those kind of molecular distribution diagrams. And of course, we can say that T red is the higher temperature, and we see T red has more, oops, it's erasing at the same time, more particles that have that energy greater than that activation energy. Their collisions will have greater energy, and that says, oh, reactions in general should get faster when they're hotter. So we have that general designation of faster versus hotter. That does not change the thermodynamics. Thermodynamics tells us what happens at equilibrium. So that equilibrium position is not changed by the rate of the reaction, but it is changed by temperature. So K changes with temperature. So this distribution of products at equilibrium is a function of temperature. And we understand that too, because we said these activation barriers are different for the forward. So here's the activation. Let me get rid of it. It's getting crowded here. So this activation barrier, this activation energy for the reverse reaction, and this activation energy for the forward are different. And in the exothermic case, this one is more sensitive to temperature. So the reverse reaction is more sensitive to temperature, and that predicted that, oh, well, if I go to higher temperatures, then I'm going to have more molecules have that much energy on this side. And that's going to affect this one. This rate changes more than that rate. And if that reverse rate changes more than the forward rate, that changes the position of equilibrium. Because at equilibrium, the rates determine the equilibrium distribution. So we do have a subtle thermodynamic and kinetic connection even here in the position at equilibrium. But position at equilibrium, if this is enthalpy, that number did not change when K changed. If it's the enthalpy. If that's the free energy, then that does change with temperature. So we have to be careful what kind of energy we're plotting there to understand that. So goodness, we have a very, very deep understanding of this, what we thought was a relatively simple picture when we started, I don't know, a long time ago. It seems like we've known each other for years. So to me, I'm quite pooped. I don't know about you guys. Well, I know you guys are pooped. I talked to a young one of your colleagues, one of your fellow students, and she's in Singapore or something, and she's taking Math 1A 2. And I think I told you the first day, don't do that. Don't try to take 2 chemistry classes or 2 summer classes. It's just crazy. And poor thing, in Singapore, trying to watch us live, so being awake at like 2 a.m. and a math and chemistry, 2 challenging courses. Goodness. Just wow. I physically couldn't do it. I have to get my sleep. And I am missing some sleep. Not so much because this, but last night I didn't sleep well. I was a little worried about the exam. As you know, they still give me a little reflow when I think about the exam. So all I have to do is write it, but I worry about you guys taking it. Okay, so let's continue now. We'll there's a few things here to discuss. I wanted to bring back the whole bond enthalpy idea. So we could calculate now. Here's the hydrogen bond energy, the oxygen double bond energy, and the hydrogen oxygen bond energy. So now we can calculate hydrogen gas, oxygen gas going to water from the bond enthalpies. Okay? If I have that chemical reaction, 2 moles or pressures of oops, I'm writing it backwards. And 1 mole of oxygen gas forming 2 moles. I should use this pen because this pen forces me to write slower. It doesn't react as quickly, and I have to write a little more neatly. And I know you guys cannot read anything I scribble on the board. So now we can say that we can put numbers in here. I'm going to break 2 moles of these 430s. So that's going to be 800 plus 60. I'm going to have to put in 860-ish kilojoules to break those 2 moles. It's 430 or 440 kilojoules for 1 mole of bonds. And I'm going to have to break 1 mole of the oxygen bonds. So around 500. I have to put in around 500. So I have to put in that much energy, and I have to put in around 500 kilojoules to break that 1 mole of bonds. I'm going to release. There are 4 moles of HO bonds. 2 HO bonds per molecule, and there are 2 molecules. So 4 times the 460 here. Released. So 4 times 4 is 1600, 4 times 2400. So this is something like 1612. So this is something like 1850 kilojoules released. I put in 8 and 5-ish, 9 and 5. I put in 1400-ish in. So I go in 1400 and out 1850. That's an exothermic chemical reaction. We know that. Is this number that I calculated an exact number? That's another thing that we talked about. The answer is no, it's not as exact as an enthalpy of reaction. So enthalpy of reaction would not include this average number. So this is an average bond energy. So we take a lot of different HO bonds. They can occur in different ways in different molecules. We take about, so they're all about 460 kilojoules per mole. So since that's an average, then this average bond enthalpies is not the exact science of the state function enthalpy of the reaction. So that's a slightly different number. What did we get? We got around, we went up around 1360 and down around 850. So that's 490-ish. So we got around, I hope I'm doing that math. I'm doing it quickly in my head. We got around 490 kilojoules per mole to form 2 moles of water. Okay, that's just a back of the envelope kind of calculation. We know it's not precise. One reason I'm just one big important reason is I suck at arithmetic, so I might have done made a mistake in there. Second is that's an average. These two are exact. There's only one kind of hydrogen-hydrogen bond, and there's only one kind of oxygen-oxygen double bond. So those are exact numbers. That's a little bit of a lie. You could have, I'm pretty sure this is the oxygen-oxygen molecule double bond. So that one I know is exact because I put it in there. You could have oxygen-oxygen double bonds. They don't occur too many places in molecules. So when you did the average, even if you did the average, most of the average would come from the fact that it's weighted heavily towards just that molecule. So something like 490, we could have done that with enthalpies of formation. We could have taken products minus reactants. And this reaction, and we'll write it up there again, 2H2 plus O2 goes to 2H2O. And we just got an approximate delta H from our bond energies of around 4, what did we say it was? 440, 490, 490. We got some approximate number for that. We could also take the enthalpies of formation of the products minus the enthalpies of formation of the reactants. The reactants are elements in their standard states. So those are 0. So this is just the enthalpy of formation of water. Enthalpy of formation of water is, we were kind of talking gas phase, 242. So does that jive with what we said? Yes. Why is that? It looks like it's off by a factor of 2. Well, it has to be off by a factor of 2 because these are per mole of water formed, and we did it for forming 2 moles of water. So we better get twice this. Okay? This is the precise number that we would tell our colleagues if we were reporting it in a scientific paper. This is the number from the bond energies that we would just calculate in the back of our heads to estimate it. And remember, we said, why do it both ways? Well, one reason to do it both ways is with just this small table, with just these few bond enthalpies, we can estimate many reactions, because if we just keep in the back of our mind what a carbon hydrogen, a carbon oxygen, a nitrogen carbon, and a carbon nitrogen bond, we can do most of our protein chemistry, or our if we're biological chemists or we're carbohydrate chemists, we can do most of the chemistry. We can estimate it with just a small table of bonds. So that's why there are the two methods, one more precise than the other. So we'll go on. Let's do a few chem quizzes. So practice for the exam tomorrow in real time. We talked about all these properties of bonds from the Lewis dot structures. We got a notion of resonance, bond order. We did this formal charge and oxidation number. The formal charge, remember, is just an accounting. These are both accounting, formal charge and oxidation number. But the formal charge is an accounting that we simply do to get the quality of the Lewis structure. The oxidation number is a slightly different accounting of electrons. So here we individually, we break up those four and say you get 2 and you get 2, nitrogen gets 2 and oxygen gets 2. Here we ionically, we distribute them, all of them, to the more electronegative element. And then we do our accounting. So two different accountings. This one doesn't have much to do with the properties of the molecule. Oxidation number is a number that we will use. That's a property of the atoms. So this we catalog and use from molecule to molecule. And this is just to judge the quality of a structure. So from our Lewis dot structure, we got this, and we got structures, we got shapes. We also talked about the polarity of the bonds and this dipole quite a bit. The polarity and the strength of bonds. So these, if we had to order these by approximate bond strength, we would say ionic, far and away strongest bond. We'd say that's number 1 strongest interaction. That's the full 1 plus charge and 1 minus charge. And there's also lattice stabilization and all kinds of other stuff, because these are usually solids and salts. Then the polar, the more polar, the stronger the bond in general, because you get some of that charge separation on top of the electron distribution holding that bond together. So pulling those guys apart, you have to break bonds, but you also have to pull those partial charges apart. Those are two things I have to pull apart. And that makes them, the more polar, the stronger the bond. And homonuclear, everything else being equal, of course, you change atoms and things are different. But in general, those are our rankings of bond strengths. Qualitatively, everything else being equal. The more polar, the stronger, and the limit of polarity is complete charge separation. So that's the one limit of polarity. This is the other end of the polarity scale, no charge separation. And in the middle, we have polar bonds. So a tremendous amount of information came out of that. Let's do some chem quizzes. So for the double ionization reaction, so I'm going to take this nitrous oxide in with a -1 charge, remove 2 electrons, and form NO2 with a positive charge. Let's talk about a couple properties. How does the bond angle and the bond order change? And notice I'm saying bond order and not telling you which bond I'm talking about. That's because all the bonds are the same. They're all nitrogen-oxygen bonds. So I can legitimately ask you for a simple molecule like this, bond order, without telling you which bond, because there's only nitrogen oxygen bonds there. So let's start our poll. You'll have to scratch things out. I'm going to give you a few minutes. Treat this like the exam, except you can ask questions among your group, which please do not do during the exam. Work on this for a few minutes and see what you come up with. Okay, guys, let's come back together on this. Oh, I didn't tell you. Yeah, entering a selection is hard because I didn't tell you which to enter the selection for. The bond angle or the bond order. I think it's the same anyway. But let's talk through it. We'll see what you guys are thinking. Overwhelmingly A. I don't know which one you're answering, bond angle, bond order, but I think the answer is the same, just looking at that in my head. So bond angle first. Draw Lewis dot structures for each. That's the only way we can get to bond angle in this class. So we do not talk about molecular orbitals and bond angle, although that is what you do if you are doing calculations on molecules. You take the atomic orbitals, you add and subtract them together, you match symmetries, and you come up with a bond angle. And by and large, that matches what you would get from a Lewis dot structure. So it's another area of good agreement. VSEPR and molecular orbitals agree to a large extent. So this is an 18 valence electron system. So I have 6 and 6. That's 12 plus 5 for a nitrogen valence electrons, plus 6 and 6 is 12 and 5 is 17, and one more because there's a charge. 18 electron system there. And that 18 electron system goes to this 16 electron system, taking away 2 electrons. So I wouldn't have had to recount there. Here's the Lewis dot structure that I came up with. So this is based on a steric number. The steric number for the central atom, in this case nitrogen, 1, 2, 3. So this bond angle is approximately what? Approximately, it's if all these were atoms, it would be 120. If there was an atom here, an atom there, and an atom there. Since this is a pair of electrons, that pair of electrons squeezes these guys down a little bit. So this is going to be something less than, something approximately less than 120 degrees. Over here, I write the Lewis dot structure, and I see when I take away that pair of electrons, then it makes sense to share that pair. So I get double bonds on both nitrogen, oxygen. So I go to completely symmetric molecule here. That completely symmetric molecule, a 16 electron system, that is steric number 2. Steric number 2 is a linear system, and linear systems always have a 180 degree bond angle. So that bond angle is 180. To do a bond angle, you have to have 3 atoms. To do a bond order, only 2. But in these cases, there's only 1 bond angle, 2. And on the exam, I give you Lewis dot structures with a central atom bonded to an equivalent number of, all the other atoms are the same that are bonded to it. So that allows you to talk about bond order and bond angle without telling you exactly which specific one to talk about. Which specific bond, okay? So that was an increase, and that's what you guys were saying. That's an increase in bond angle. Just wanted to point out that these 2 structures are isoequivalent. electronic. We talked about isoelectronic for atoms and ions, the same number of electrons. You can have isoelectronic molecules as well, because when we talk about molecules, we talk about the valence electrons when we're doing Lewis dot structures. So we're still adding up valence electrons, so you can still have isoelectronic. And the famous 16 electron 3-body problem is linear double bonded. So both NO2 plus and carbon dioxide have the same Lewis dot structure. So isoelectronic structures in general have the same Lewis dot structure, and that can often save you some time. Won't save you guys much time because you don't do this enough. You don't become chemists and write things that look the same. Okay, so that's the bond angle story. What about the bond order story? Bond order, I'm going to look at this. That also increases, and I think you can see that without even doing a calculation. Here I have 2 double bonds. Here I have a single bond and a double bond. So the NO bond order, which is the average of all the resonance structures. So it's bonding electrons. Oopsie. I don't have an animation, so I have the bond order is bonding electrons here, electron pairs over the number of bonds that are sharing those pairs. So 1, 2, 3 electron pairs shared over 1, 2 bonds. This is 1.5 bond order, and this one is obvious. That's bond order 2, I think. Okay. We had another way to do bond order. We did it with our molecular orbitals too. So you're going to say, Mark, because you all know me personally and we're on a first name basis. I feel like we're on a first name basis already. I welcome everyone, of course, to call me Mark. The bond order from our molecular orbitals, we saw generally agreed with this Lewis structure bond order, but we calculate it by looking at the bonding and antibonding orbitals. So we did it in a slightly different way. You'll say, Mark, how do I know which way to use when I'm on the exam? And it will be obvious from the context. If you've just drawn a Lewis structure and I ask you for the bond order, get it there. If you've just filled a molecular orbital diagram and I ask you for the bond order, get it from that. In general, same number. They should be about the same number anyway. Okay, we looked a little bit more about structure. So here, what about the oxidation number and the bond order? So this process, so I'm going to look at just the oxygen molecules, 2 different reactions, and say, what about the oxidation number and the bond order? Let's not worry about the bond order right now. Let's just talk about the oxidation number for oxygen. As a reactant, oxygen gas, or as a molecule, NO2 minus gas. Oh, NO2 plus or NO2 minus. Make sure they're different reactions. So these are the same 2 molecules we had. So that means we don't have to fart around and redraw the Lewis dot structures, which I know you hate it, but this is why I do one table with a lot of questions. So in general, you're thinking about the same thing. But I will tell you, and this is important, when I give you that one table and a bunch of questions, I always make sure they can be done in any order, and you should not have to use the answer from one thing to do another thing. That's always the case. You can start from scratch on any single related question and do it in any order. And of course that matters because, as you know, the system randomizes the order and even randomizes the questions. The bank of questions that we pull from is larger than the number of questions on the exam. That's so not everybody has the same exam. As you know, you always click a version as you, if you say that too fast, you click a version at the beginning of the exam. I always click a version. I'm averse to all exams. Get what I did there? Aversion. I crack myself up. I wish, sometimes I wish you guys were here to see if we cracked you up too. It's probably more groaning than anything else. So let's look at the oxidation number. We know what these things look like now, so I can draw that Lewis dot structure. That one I know well. What is the bond order I would get here? 2. What is the bond order I would get there? 2. We're more interested in oxidation number. What's the oxidation number in oxygen, the molecule? Oxygen, the molecule, of course, if it's homonuclear, the oxidation number is 0. So elements in their standard states have oxidation number 0. That's something you can grab onto. I know that there's so few things that you can take to the bank. We're taking a lot of things to the bank, though. If you take nothing else home from Chem 1, take home. It always takes energy to break bonds. Oxidation numbers of elements in their standard state are 0. The energy of a gas depends only on the temperature. Those are 3 that come to mind right away. Maybe you guys can chant other ones. I hope you can, because I think there's 1 or 2 more. So here, though, the oxidation number of oxygen is different. And so that is a decrease in oxidation number from 0 to -2. Okay. Oxygen is reduced in that chemical reaction. Nitrogen is oxidized in that chemical reaction. So let's do the nitrogen. The nitrogen, we don't even have to draw the Lewis dot structure. That's nitrogen in its standard state. It has oxidation number for nitrogen in N2 is 0. Oxidation for nitrogen over here. Now we kind of need the Lewis dot structure. We don't really need it because we already got oxidation number -2 for the oxygens, and they're both the same. So if this is oxidation number -2 and that's oxidation number -2, then the whole thing has a plus charge. So this must be +5. So that -2, 5, and 2 add up to +1. The oxidation numbers add up to the charge on the nucleus. So I can get the oxidation number there, +5 for nitrogen, just by math. Or I can say, well, the way we do it is oxidation number, the electronegative element greedily grabs all the electrons. So the more electronegative element is oxygen. It greedily grabs those, and then we calculate. Oxygen normally has, oxygen as an atom on the periodic table has 6 valence electrons. So this is the atom. In the molecule, so switch back and forth. I think you are switching back and forth, Sydney, so they get good views of this. In the molecule, oxygen has how many around it? So 6 around it in an atom. Here, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around it when we do our accounting here. And that, fortunately, is where we would have got that -2. 2 more electrons than it would have as an atom. So 2 extra negative charges, -2 charge. Nitrogen as an atom has 5 valence electrons. We can get that from the periodic table. Here it has 0. The oxygen stripped all of them away. And there we also get that same number, +5. Okay, so the oxidation number decreased in that for that one, decreased for oxygen, increased for nitrogen. And of course, that has to happen. If one oxidation number increases somewhere else, an oxidation number must decrease because the number of electrons is conserved. What the oxidation number you can kind of tell is where are the electrons assigned, and it's the same number of electrons. So oxidation numbers have to add up to charge, and if something is oxidized, oxidized means increase in oxidation number, so the nitrogen is oxidized. Something else had to be reduced, reduction in oxidation number. And in this case, it's the oxygen which is reduced from 0 to -2. It's the nitrogen that is oxidized from 0 to +5. It also kind of looks like the nitrogen is oxidized. No oxygen's attached, and then oxygen's attached. That is another definition of oxidation in general. Things can be oxidized in the absence of oxygen, but if oxygen's involved, the more oxygens you attach, the more oxidized you are. Oh, this is the other chemical reaction. Here I just wrote out this one because the bond order on oxygen stays the same, but the bond order, overall bond order, is reduced. It went from bond order 2 to bond order 1.5. Oxidation numbers don't change. Interestingly, there. Okay, 2 different reactions. Okay, let's talk again in our small groups and scratch out. Let's not. I'm talking too much. Let's do. So we just did a bunch of Lewis dot structures. We've done a bunch of structures, bond angles, all that. Let's just jump ahead now because we're running out of time here. Let's do a molecular orbital calculation. So we can do that, and I'll talk through a few of these because I do want you to see a lot of stuff. You can work them out on your own when you get. Oh, here's what I'll do. Stand by. We'll go back to where we were. I'm going to page through a bunch of chem quizzes here because they're all good chem quizzes. And if you'd like, you can review this video or you can take a screenshot right now. In fact, I'll work with Sydney. Sydney, switch back and forth, give them this. Go ahead and screenshot that if you'd like. Work on that on your own. Great review for the exam. I will. You guys will just be angry if I skip the answer, won't you? I'd rather have you work it out on your own and ask your GSIs or something, but the exam's tomorrow. So see if you get the same answer. Oh, I have to go through all the animations. Oops. See if you get the same answer that I do. So you can screenshot that or save that. And now we'll move on to our molecular orbitals. So we can do one of those. I'll talk through it with you. Which paramagnetic species has the weakest bond? So read the question. Which paramagnetic species has the weakest bond? Paramagnetic means unpaired electrons. And read the questions carefully. You know that for the exam, we're going to go back and draw questions from your homework, but we are going to change them just slightly. So the answer is not exactly the same, but exactly the same concept is tested. But read carefully. You might recognize a question because you saw it in your homework. Don't answer exactly like you did in your homework. I mean, it might be the same, but read carefully work through it and make sure it is the same, because we are changing them. And that messed up a bunch of people. Some people, even the highest grades in the class, we had one last time where I changed the word velocity to momentum, and half of you got it wrong because I think you answered how you did in the homework instead of reading it. I was talking about momentum now, not velocity. Mass times the velocity. So read carefully. Which paramagnetic species? So let's go through that. Here are these molecular orbital diagrams, and remember, they will be provided for you. You do not have to memorize these ordering of bonds. The ribbed structure of an athlete's abs. You don't have to memorize these. They'll be given to you because they change based on the species. So we'll have to give it to you. So here I have F2 plus. Is there more animation here? Nope. I asked which was the weakest. So the weakest, you can kind of just look at the weakest, since they're all the same, basically. This is going to tell you what is the weakest bond. The more anti-bonding electrons, the weaker the bond. And since they're all identical below that, the only thing that's changing is the antibonding electrons. So more antibonding electrons, weaker bond. So why isn't the answer this? That has the most, because that is not paramagnetic. We asked which paramagnetic species has the weaker bond. So read carefully. I'm going to emphasize one other thing here, and that is, since only the upper things, matter, the top, essentially, when you're comparing a couple different things, just the tops of the molecular orbital diagrams matter. So I'm frequently, and in fact, I know this for the case, on the exam, I didn't even show you the lowest two because they're full. But you need to be careful that you account for this as you're filling up your diagrams. In fact, I should just go back and put them in. I think I might do that. Let's not make it harder than you are. I'll give you a full diagram. There was a reason that I did not give you the full. I'll go back and check. If you just see the top, recall you still have to put in all the valence electrons. So recall, if I don't go change it, that there's sigma, and these are from the S. These are from the S electrons, or S orbitals. So these are the S valence electrons, and then the P valence electrons are here. I don't think I'm going to go change it on the exam because it's dangerous to change things at this stage. That might change answers and get a mess. So S and P electrons go in different parts of the structure. I did not show you on the exam the S part of the molecular orbital diagram, just the P part. So be aware. Still got to use all valence. Put the P valence electrons in the top part. Okay? Glad we went over that. People who aren't here today will be bummed they did not see that. Okay, we talked about bond orders a lot, so let me go back. This is a hybridization question. How do you hybridize? And if you can just show them this one on the board, you can take a screenshot of this and see if you can do this. I'm not going to go through this one with you. How many carbon p orbitals are used to form the pi bonds here? So I have a pi bond here. There's a pi bond there. You should be able to identify the pi bonds. I'm not sure I said that very clearly yet. In any molecule, you should be able to identify the pi bonds from the Lewis structure, believe it or not. because the first bond is always a sigma bond. And if there are any other bonds, they have to be pi bonds. Okay? So one of these, I don't know which one because it's just a line, but one of them is a sigma and one of them is a pi bond. Okay? So here I have alternating pi bonds here, single, double, or double, single, double, single. So there are pi bonds there. So that means this carbon and that carbon have to do some pi bonding, and this carbon and that carbon don't have to do pi bonding. So this guy and this guy have different hybridizations. They're using their orbitals differently to do that. They all have the same hybridization. This guy doesn't have the same hybridization when I get there. All these carbons, except for that one, are sp2 hybridized. They all have steric number 3, except when you get to that one, that has sp3 hybridization. It cannot make a pi bond. How do you make pi bonds? With the p orbitals that are left over as you do your hybridization. There cannot be a pi bond, and indeed, those are all single bonds. So these bond angles are around 109 degrees. These bond angles are around 120 degrees. And how many pi bonds, how many p orbitals are used to form the pi bonds? 1 pi bond, 2 pi bond, 3 pi bonds. Okay, so for all those 3 pi bonds, I need orbitals to do them. Carbons 1, 4, 6, and 7, sp2 hybridize. That's 6 p orbitals required to make 1, 2, 3 pi bonds. Remember, to make a pi bond, bonding orbital, I get a bonding and an anti-bonding. So I need 6 p orbitals to make 3 pi bonding and anti-bonding molecular orbitals. Okay. That's all summarized there. We didn't talk about delocalization, so that was for another day. Oh, here's a good one. Go through. So here you need to ponder what direction those orbitals are pointing. So take a screenshot here. Sydney will show it to you. You get a good screenshot and see if you understand what's going on there. Where is the pi electron density relative to the plane of the molecule? That's planar, sp2 hybridized. That's a good one. Talk about that one. Here are the molecular orbitals overlapping to form atomic orbitals overlapping to form molecular orbitals. Which one has the highest energy? The ZZ, the XX, or the YY? Given the internuclear axis is Z, on that one. That one's not as important, I don't think. I want to get to some, I'm going to skip through all these. I want to get to some phases and energy. So we talked about the gas phase. So we have our PV equals nRT kind of stuff. Maybe we'll skip that review because that is the easier part of our gas. We'll talk about it a little bit, but here is PV equals nRT. PV equals nRT for 1 mole N. And we saw we got the kinetic energy of a mole, the total kinetic energy of the system, goes as a function of temperature. If you take nothing else home from Chem 1, the energy of a gas is all kinetic, depends only on the temperature. And the number of moles, if you have, it's still extensive. So 1 mole, if I talk about the total energy of a sample of gas, I have to know how many particles. So 2 moles of gas has twice the energy of 1 mole of gas. So if that's not an N0, you'd have to have an N here. Kinetic energy, so this is kinetic energy per mole. Multiply that by the number of moles to get the energy of a sample if you have more than 1 mole. Here, the average kinetic energy per molecule So that tells you about, what the average molecule has, individual particle. And there we use Boltzmann's constant, which is just the gas constant divided by Avogadro's number. We came to this thing called the RMS speed, root mean squared speed, and that characterized our distributions, our Maxwell-Boltzmann distributions. It gets bigger with the temperature. VRMS gets larger. So the distributions spread out as temperature goes up, and as mass decreases, they spread out. VRMS, the root mean squared speed, gets bigger. And the general thing, pretty much the only thing that I ask you very much about at any time for the distributions is essentially that. So if we're going to take a distribution of the number of particles versus their speeds, and we know this is also their energies, because those two things are related, it's all kinetic. The two things I ask are pretty much the one thing that I ask you the most about is just how the shapes change with temperature and mass is really what you saw that in all the chem quizzes. And that's characterized by the VRMS. So you should know where VRMS qualitatively falls. That is, I don't know the exact position, but qualitatively it's higher than the most probable velocity. And if that increases with temperature and mass, that means the red one is either a higher temperature or lower mass. And we talked about phase changes. So which is the pressure temperature isotherm if I'm showing you a pressure volume isotherm? So along this line, the temperature doesn't change. And these plots, if the temperature doesn't change, the line has to be vertical, one temperature. So the pressure can change without changing that. So which of these corresponds to that? So if I took all the points on this line and I used PV equals nRT to get if I calculated all the PV there, I would get a bunch of different pressures. How would those pressures use PV equals nRT to get the temperatures here? How would those look? These are, you have to scratch your head on, but I don't make this complicated. I want you to know conceptually what's going on. You should recognize that conceptually as a condensation occurring. Okay, this is a real gas behavior. So if you see this odd shape to the isotherm, that's because there's a condensation or a vaporization, whichever direction you're going. Condensation. So that must be a real gas. Intermolecular forces are coming into play. If you're above the critical temperature, your isotherms start to behave like ideal gases. PV equals a constant. For a constant number of moles, that constant is nRT. At a constant temperature, that's an isotherm. So if both N and T are constant, P is 1 over V is what you plot there. P is a constant. So there are all the answers for us. At A, that's what it looks like. A, I started a gas. I do a phase change right here. The solid or the gas and the liquid are in equilibrium, and then I go to the liquid phase. Okay. Decreased pressure at constant temperature. I go from the gas to the liquid. That's a phase change that occurs here. This one is at the critical temperature, so I barely see a phase change. Don't have that sharp change, and then above, see the critical temperature it behaves ideally. P times V is a constant. Okay, take home lesson. If we had the bell, we didn't do the bell. Shoot, forgot about the bell. Did you guys like the bell last time when we did ring a bell every time something kind of exactly appeared? Like, or these guys did the exam. They're all doing the ring the bell motion on this. So apparently that's on there. Exactly. Almost, I mean, I know intimately what's on the exam, so I am saying things myself that are there, but the exact things, it's fun to ring the bell. We'll have to do that next time. Remind me to do the bell. If you like the bell, tell us you like the bell and remind us, ring the bell for the exam concepts. In fact, in general, I'll do the vlogger thing. I'll pretend I'm a YouTuber. If you like what you're seeing, like and subscribe. I'm joking. Of course, I'm joking mostly, but not all together. If you like the way this course is presented, there's a little bit of movement on campus to get our online courses to look more consistent and nicer. So if you've seen a lot of online courses and you okay, good. Andrew says you're all saying ring the bell. Good, we will do that. But remind us if we start next time and don't have the bell, remind us to get them. But like and subscribe, really. Subscribe to the channel. It doesn't make much difference for you. But what campus is going to do, and administration, and I'm talking to our dean about this, is let's get some student impact. What do you guys like it? Like and subscribe if you do, and that will, it doesn't get us any more advertising revenue. So I'm not a real YouTuber, but it will make this more courses look like this. If you don't like it, and you'd rather not have this, and of course, don't like and subscribe, vote with your finger. Okay, one person is subscribed just by that. Click like and subscribe. Okay. Which plot corresponds to the process shown? This is doing the reverse thing. So now I'm above the critical temperature. So I know above the critical temperature, I get P looks like V. P times V is a constant. So that's the same kind of thing. Which is the appropriate energy, total energy of the sample versus temperature at constant pressure for 2 moles of neon and 1 mole of argon? Okay, if you take nothing else home from Chem 1A, take home the fact the energy is 3/2 RT per mole. So if I have different number of moles, I have to put N in there, but it's always linear. So if I'm going to plot for the ideal case, if I'm going to plot the kinetic energy versus temperature, these better be straight lines. E versus T, a constant for a constant number of moles at a constant pressure. So in that case, N is different. So we had 2 moles of neon. We had 1 mole. I have the eraser thing. Argon. We had 1 mole. So the slope is different, factor of 2 between the slopes, because there's 2 moles of neon and 1 mole of argon. So neon has the steeper slope, the greater slope. So neon and argon look like that. And here, you notice I probably didn't have, I put exact, we rarely do this, we rarely give you exact numbers. These are usually just qualitative. Here I did it quantitatively. This was actually more for me, so I could make sure the slopes looked like about doubled. But you could look at them yourselves and see if the slopes doubled. Oh, here's a good one. Now let's do it. Let's do kinetic energy versus volume of those 2 gases. Oh, goodness. Can you plot that? Oops, there's the answer. If we plot that, now it's kinetic energy versus volume of the gas. How does that go? And sometimes, you know, it helps to do the math. Sometimes it helps to just think about it. It's hard to just do the think about it when you're just starting. I know. A concept takes time to digest, and that's why summer Chem 1A is so difficult. I teach this very conceptually because when I teach it in the fall, we have twice the amount of time and the concepts can sink in. And how do concepts sink in? You think about it, but you also do some math and you compare the math results to your intuition and you get that intuition and you start to understand the concept. I said to you this before once already. I don't know if I'm going to teach this in the summer again because it's just not fair the way I teach it. There's no way anyone can absorb it, especially if you're taking math 1A at the same time. Forget it. But you could think about this conceptually. You may be at the point where you say, well, I want the kinetic energy. I know what it is per mole. And I'm going to say, well, what if I keep taking a bigger volume now? So I take this much, then I take this much, then I take this much, and I keep the pressure constant. And I just keep taking more volume. The energy is going to go up because I keep getting more particles. I keep grabbing more particles, so it's going to go up. And if I take a box twice the size, twice the volume, I'll get twice the neon particles as the argon particles because neon has twice the pressure, isn't that what, or twice the number of moles? It has twice the number of moles per volume as argon. Its pressure is twice as big. So that's the conceptual part. The relationship I think I've tried to describe is the same, but we can do the math. If the kinetic energy is 3/2 nRT per for the sample, and PV equals nRT, that's our nRT. So just put PV in there. And for constant pressure, the energy is linear with the volume. The initial pressure, or the pressure twice the neon as the argon, because there were twice the number of particles in the neon as the argon. Okay? Okay, wonderful, guys. Good luck tonight. I'll hang here for a few minutes if there are some. We have a staff meeting, so we kind of have to talk about this, but I'll hang here for a few minutes if there's some pressing questions. Go ahead, ask them in the chat or in the Zoom. You can bring the Zoom together if you'd like, Andrew. And Andrew, you monitor the Zoom audio and just ask me if there's some good questions coming in. Just ask me. Oh, you don't have your headphones today, do you? Okay. Or Lillian, just turn your mic on. So if you have questions, you can ask them. It's quicker that way. Just ask them. Lillian and Andrew are monitoring. They'll relay to me. Or if you feel like typing a vital question into the YouTube chat, you can do that as well. But we can take 10 minutes here and see if a good question or two comes up. I'll filter the questions, and they will too. Let's get the best questions coming in. Go. Question coming in: how do we know how many p orbitals or how many pi molecular orbitals are formed? Those things are going to be related. The kind of question you're going to see is count up the pi molecular orbitals and say how many p orbitals it took to make those. Every pi molecular orbital takes 2 p orbitals to form it. Orbitals are conserved. If you form a bond, you get a bonding and an anti-bonding orbital. Mm-hmm. Mm-hmm. So if you form a bond, any kind of bond, whether it be pi or sigma, you get two, they're all composed of two molecular orbitals. One of them bonding and an antibonding. And orbitals are conserved. So if I'm going to make a, we were talking here somehow. Palm mode on. I like to be able to erase with my palm. I'm not sure how that got turned off. Now I can erase with my palm. So if I form a pi bond, then there must be a pi star and a pi molecular orbital in there. And that comes from two p atomic orbitals. And in this case, it comes from one on each of the atoms that are in the bond. So I can always easily count. Here's benzene. 1, 2, 3. I can count the number of pi bonds in that molecule because pi bonds are all the double bonds. If it's a triple bond, then there's 2 pi bonds and a sigma. If there's, I can also grab and move stuff. I'll just get that bond out of there. If there's 2 bonds, 1 sigma, 1 pi, 3 bonds, 1 sigma, 2 pi's. So there are 3 pi bonds. There, I need 6 atomic p orbitals among 6 atoms because 1 comes from each atom in the bond. Okay, so that's 3 pi bonds, and they're coming from 6 p orbitals on 3. In this case, these are all carbons. Okay, good question. Other things? The question is, do the graphs of steric repulsion always reach a plateau? I think I understand what you're talking about. So if we talk about the interaction energy versus separation, r, the radius, the distance between two things. So I'm talking about this situation, or I have this thing and this thing, and this distance is r. Oops, I made a little r there. Then do those always reach a plateau, I think is what the question is. So their general shape looks like that. And I think the question is, do they always reach this plateau? I like that as an exam question. You have to remember that one too, because you should know the answer. Kind of. Maybe it's too hard an exam question. The answer is yes. They always plateau out to 0, because as you go farther and farther away, that interaction energy has to go to 0. If they're far away, they don't see each other. There's got to be 0 interaction. And we set that as the 0. I've said that many times. 0 in energy is infinitely far apart. So I think that's the question. You can put into the chat that that wasn't the question. But if that's the question, then yes. Good question. I like when people are thinking about the plots. And of course, you're kind of forced to think about them because I'm always putting them on the exam. Other things? Oh, I blew through a chem quiz that had CN minus. The question is, how do I know the hybridization on a molecule by looking at the Lewis structure? Yeah, carbon, nitrogen, the cyanide ion has a negative charge. And I guess the chem quiz asked for the hybridization of the carbon. Hybridization always comes from steric numbers. So you don't have to draw Lewis dot structures. You don't have to count sigma and pi bonds. Just get to the steric number. Okay? Steric number on this carbon is 2. It has to accommodate that lone pair, one thing, and this atom, 2 things. Don't count bonds when you're looking for the steric number, just the things. That lone pair and that nitrogen. And that always gives you, there's a 1-to-1 correspondence. If you're a mathematician, you say if and only if. If and only if in math means it goes both ways. This has to be sp, how many things? I need 2 orbitals. That has to be sp hybridization. Okay, so if and only if your steric number is 2, if and only if you have sp hybridization. If you have sp hybridization, if and only if you have 2. And of course, you know that table. If you go to 3, the number of orbitals just has to add up to that. So 1, 2 orbitals, sp2. Steric number 4, sp3. 4 orbitals, 2 orbitals, 3 orbitals, 2 orbitals. Okay? Take that one home. Quiz your friends, if and only if. No, don't do that. You'll look silly. Other things? Whether the pi electron density, where the pi electron density sat in that formaldehyde. Yes, I think that's probably what they're asking. There's a chem quiz where we said formaldehyde, carbon, oxygen, hydrogen, steric number 3, sp2 hybridized, guaranteed. 1 sigma bond, 1 pi bond. All that stuff I can get. If I draw the electrons there, oops, too many. Oops, my eraser stopped erasing. Oh, the pen is too close. Steric number 3, 2 lone pairs and a carbon. sp2 hybridized, sp2 hybridized. Hydrogen doesn't hybridize. The question was, where are the pi? So if that's a plane, that's the plane of the molecule, is the plane of the board. And on the chem quiz, I switched it a little bit and I drew the plane like that. So in that plane, the carbon and the oxygen and the 2 hydrogens are in that plane. I just flipped it like that. I asked where the pi orbitals are. Pi orbitals are always above and below the internuclear axis. So they're there. So the sigma bond is in the plane, and the sigma bond is an overlap of an sp2 on the carbon with an sp2 on the oxygen to form a sigma and a sigma star molecular orbitals. These are atomic. These are molecular. You have another p atomic orbital left over. So you have a p orbital on carbon and a p orbital on oxygen left over. They form the pi and the pi star. And where are they? Intuitively, I think you might have said they better be above and below the plane. There's a plus side of the wave function and a minus side of the wave function and a node along the internuclear axis. That has to be the case. Why? Because that's where there's the room for them. And if you start doing all your axes, so this is a plane. So if this is the XY plane in yellow, then this is Z. And if I have to do all the bonding in the XY plane, I'm going to use the PX plus the PY on my atoms, because I got to be in that plane. That leaves the PZ left over there above and below the plane to form the pi bond, the second bond. Another way to think of it, well, there's not room. I mean, how the pi bond's gonna run into those hydrogens if it's in the plane. So another way to maybe think about it, but this is the best way to think about it. Use up your orbitals and see what's left over. And that's always the case. The pi bonds are always above and below the plane of the molecule. Okay. All right, we'll end it there. Good luck. Your GSIs or your UGSIs are around, I think. There's office hours left. The Student Learning Center is available. I think they have some sessions. Good luck tonight. We'll see you tomorrow morning.